All right, IBAASL2 kids. Today we're finishing off 5.5, which means we are talking kinematics. Now, during this lesson, you're going to be like, wait a minute, is this physics class? Which it kind of is. I don't know if you guys know this, but a lot of math is used in physics, and a lot of it is sort of calculus-based with derivatives and second derivatives. So, before we get into our one big problem for the day, we need to define some terms. A path is a set of points on which an object travels. So you're going to be given some equations where it's like, this particle or object travels in this way with this equation. Distance traveled is the total length on that path, whatever it may be. The displacement is slightly different. Displacement is just the difference between a position and a fixed point. So a lot of times it's like, how far was the object displaced in terms of, from the start to the finish or something like that. A classic example of that is that if you run, let's say you're running track and you start right here, and then you run on a big track and you go all the way around, that, this entire lap around it might be, 400 meters or something like that. That's how much you traveled going around, 400 meters like this. But your displacement would be 0. So displacement is 0 because you're back in the same position that you started in. So you didn't, if you ended a little bit past there, like your displacement would be this distance right here. It's however far you are from your starting point. So, for instance, if you have a distance traveled on this diagram between A and B, like if a particle takes this path right here, then this is the distance traveled. But if they ask the displacement of the particle from A to B, the displacement would just be a straight line between the two. So this is your displacement. Couple of other terms you may have heard in science class. Velocity is going to be the derivative of the displacement function. So usually you're given some sort of master function that shows like the path of a particle or the displacement or the distance traveled. That's usually like s of t. So if you take the derivative of that, that's going to be v of t. Another way to say a derivative is ds dt, derivative of s with respect to t. And, of course, we've said that as s prime of t. Now, if you take the derivative of the derivative, so take the derivative of the velocity, you are going to find acceleration. Acceleration is the derivative of velocity. We'll just call it a of t. Know that you could call it the derivative of velocity with respect to t, or you can say it's the second derivative of displacement with respect to t. That's what that funky notation means with the d squared s dt squared. It's just a funny way to say the second derivative. Of course, you can say it the way we've been saying it the whole time, which is just s double prime of t. When V and A have the same sign, that means it is speeding up, and that is called accelerating. So if you have t when time equals 4 or something like that, and you plug it into the first and second derivative, which are velocity and acceleration, if they're both positive numbers or both negative numbers, that would mean that it is speeding up. So it could be positive or negative. If you stick a t-value into both velocity and acceleration and they get opposite signs, opposite means that it is slowing down, aka decelerating. So that would be positive with one, negative with the other, or negative with one, positive with the other. Okay, time for our big example. A particle moves in a horizontal line, so its position after t seconds, of course, time is greater than 0. What do you think we're doing? Negative time is set by this equation right here. S of t equals 5t squared minus t to the 4th. A quartic. S of t is going to be measured in meters. First up, I think to wrap my head around this problem, I think of like a particle starting here, and then it anytime s of t is positive, it moved to the right. And then anytime s of t is negative, it moved to the left. So I almost picture it like this particle that starts here, and then it zips over to the right, and then it zips back over to the left, and then it zips back over to the right again, and then over to the left, and to the right, and to the left, and to the right. And it just keeps going back and forth, and it's modeled by this equation. Find position, velocity, and acceleration after 1 second. Well, position would just be the master equation, but velocity and acceleration are the first and second derivatives of that. So first, we're going to do s of 1 is equal to 5 times 1 squared minus 1 to the fourth. And then we're going to do velocity of 1. Remember, velocity is the first derivative of s of t. So that'll be 10, 1, minus 4, 1 to the third. Now I did two moves at once because we've been taking a lot of derivatives. I took the derivative of s of t and I plugged a 1 into it because that's what we're going to do. I guess I could have started with the equation. Then acceleration, which we call lowercase a, is going to be the derivative of the derivative. So let me see, that part goes away and we just get 10 minus 12x squared. So it'd be like 10 minus 12, 1 squared. Now, the top equation is the position equation. So that's it. When you take 5 times 1 squared is 5, take away 1 is 4. So this is going to be 4 meters from its starting point. That's its displacement. The velocity is going to be, let me see, 10 take away 4 is 6. And then this is going to be meters per second. So your book is going to do something like this, ms to the negative 1. But remember, that's the same thing, like that negative 1 on the power could go downstairs. So that could be just meters per second is the other way to say that. The acceleration, 10 take away 12, is going to be negative 2. And then this is going to be meters per second squared. So this is ms to the negative 2, which is the same thing as negative 2 meters per second squared. So that's your position, velocity, and acceleration after 1 second. Now, is the particle speeding up or slowing down? You need to look at signs of velocity and acceleration. Remember, I just showed you guys if they match, they're speeding up. If they don't match, they're slowing down. So, because here, 1 negative and 1 positive, that means it is slowing down. Right? Yeah. All right, so far so good. Find the values of t when the particle is at rest. The particle being at rest is basically like if you think of the velocity, it's like, you know, this particle is moving back and forth left to right. So it's like particles here, and then it goes this way, and then it turns around, and then it goes back this way, and then it turns around, and then it goes back this way. So anytime it's at rest is when your velocity is going to be equal to 0. That's when it slows down and turns around and then goes back the other direction. So we need the velocity equation, which is the first derivative, which is 10t minus 4t cubed. And we'll set that equal to 0 and try to solve, because that's when it's turning around. It's a turning point, just like on a graph. Let me see, let's factor that bad boy. 2t, and then we'll do 5 minus 2t squared. So then when you set them both equal to 0, you get 0 is equal to 2t, and 5 minus 2t squared is equal to 0. So So then here you get t is equal to 0, and then you subtract 5, you divide by 2, so you get t squared is equal to the square root of 5 halves. No, not t squared. I took the square root, so t equals equal to 5 halves. Now you might be looking at that and being like, jolly, did you just take the square root without putting plus or minus in front of it? Man, I've been waiting all year for you to slip up. It finally happened. Yeah, but I didn't slip up though, because t is time in this case, and they said in the beginning time couldn't be negative, so we're just taking the positive time. Nice try though. So yeah, these are the two spots where the particle is at rest. Part D, find the time intervals when the particle is speeding up and slowing down. Speeding up and slowing down has to do with, that's not the right thing, acceleration, which is our second derivative. When it changes from speeding up to slowing down is when the second derivative signs change. So I need to figure out when there's sort of, you can think of it like an inflection point, but it's basically when the second derivative equals 0, because then I can do my zone test to figure out what's happening in the zones. Yeah, we need to figure out when the second derivative is equal to 0, and then use that in a zone test also with these points here. So first, let's look at the second derivative, which is a of t. And a of t was 10 minus 12t squared. When we set that equal to 0 to figure out when it changes, you subtract 10, divide by 12, which is 5, 6. So then you take the square root. Once again, we don't have to do the negative because it's time, so it can't be negative in this case. So we have to do this big zone test thing. On the zone test, we have time starting at 0. Then there's a change at root 5, 6, because that's where the acceleration turns around. But then we also have to include our answer from up here, the square root of 5 halves, because that's when it physically turns around. It's not just the acceleration turning around. So that is square root of 5 halves, which I'll just put right here, because I know square root of 5 halves is bigger than the square root of 5 6. You could turn them into decimals on your calculator to see that. Yeah, so we have these 3 zones. I kind of don't like where I put that. I'm going to space it out a little more because I need room to write. So we're going to do a zone test, but the zone test has to be for acceleration and velocity, because if I want to figure out when it's speeding up and slowing down, that's whether or not the velocity and acceleration signs match or don't match. So what we'll do is pick numbers from this zone, and this zone, and plug them in to the acceleration and the velocity. If I take the square root of 5 divided by 6, that's about 0.91. So I'll just make a little note to myself that that's about 0.91. And then the square root of 5 halves, that is 1.58. Hey, that's good news because the number 1 is right in between them. So I'll probably choose like 0.5, 1, and 2, and plug those in. So first, I will put a velocity on this line and acceleration on this line. When you plug in 0.5 into the velocity equation, you get a positive number. So this is plus. When you put 0.5 into the acceleration, well, I guess I could write these somewhere. So like velocity of t is equal to 10t minus 4t squared. Cubed, I mean. And then a of t, acceleration, is the second derivative, is 10 minus 12t squared. I guess I had it right there. When you put 0.5 into acceleration, you should get a positive number as well. And then if you put 1 into both of those, in the velocity equation, you get a positive. In the acceleration, you get a negative. Then when you put it 2 into both of them, I believe they're both negative numbers. So check it out. We got matchy-matchy right here and right here. So in those zones, it's speeding up because if it matches, it's speeding up. In this zone, they don't match. So this is up, up, and this is down. What do we do in IB notation? Oh, they switched it. They went alligators. Cool. So final answer, speeding up when t is in between 0 and square root of 5, 6, and when t is greater than root 5 halves. And then speeding down, slowing down. Sorry, I'm running out of room, guys. In between root 5, 6 and root 5 halves. So all right, that's what's speeding up and slowing down. So you had to test it both in acceleration and velocity to see where they matched. Last problem, find the total distance traveled in the first 3 seconds. Okay, we know from the first derivative, the velocity derivative, that after root 5 over 2 seconds, that it changes because, yeah, I guess we should say t equals root 5 over 2 is a turnaround point. So we need to figure out, that's picture that it's like the particle moved to the right or left, root 5 over 2 seconds, and then it turns around to go back the other way. So we need to figure out that distance it went in the first little section. So in the OG equation, we're going to do s of root 5 over 2. Okay. Get your 5 right, Jolly. In the OG, so the OG was 5 times t squared minus t to the 4th. So this would be 5 times root 5 over 2 squared minus t to the 4th, but t is root 5 over t. Get that square root all the way around. Squared. No, to the 4th. Come on, you've come so far, just finish it. If you crunch that out on your calculator, or you could do it by hand, but they did calculator for sure, it's 6.25 meters. So that means it went 6.25 meters to the right. But then it turns around and goes to the left. So if you picture this on like a number line, it's like here, if it's starting at 0, it went 6.25 this way, but then it's going to turn around and go back the other direction. So we need to figure out how far it goes from root 5 over 2 to the 3 second mark, because that's, within the first 3 seconds. So we also need to find s of 3. So we do 5 times 3 squared minus 3 to the 4th, and this is negative 36 meters. So that means it went 6.25 meters to the right in the first root 5 over 2 seconds. Then it goes 36 meters to the left in the next 3 seconds. And we're going to do total distance. So let's think. It goes... Oh, that's negative 36. So that negative 36 part, here, I'll clean up my diagram so you guys can understand what happened, is like it went this direction, but the negative 36 is just this right here. So when it went back the other direction, it backtracked on the 6.25 and then went another 36 meters that direction. So let's think. For the first section here, it went 6.25. Then it went back another 6.25. We're just doing total distance because it had to backtrack here. Another 6.25 to get back to 0. And then it went another 36 meters to the left. So you can think of it like an absolute value that you're just adding the physical, the actual positive distances together. So when you add all of those together, I believe we get 48.5 meters total distance traveled. And we've done it, you guys. Man, that was one physics kinematic acceleration problem. All right, you guys, good luck.